In this video, we're going to talk about repeated measures ANOVA, which I'm sorry to say is a little harder to understand than a dependent t-test, so we're going to take a while on this. So the introduction to this, it is an ANOVA, so we still have more than 2 levels. So we still have a categorical IV, but it has more than 2 levels. If it only had 2, it would be a t-test. The main thing here, it's in the title, it's a repeated measures. So it's the same thing as a dependent t-test. It could be the same measure given more than 2 times over a long period of time, or it could be different measures given to the same participants. It's the same thing as a dependent T. This is a within subjects design. This one-way ANOVA has, the one-way ANOVA was called a between subjects design, but now we have a within subjects design. Sample participants are tested on every factor level. It's still a one-way ANOVA because there's only one factor, but now it's a one-way repeated measures ANOVA. We just usually drop the one-way from the front of it and just call it a repeated measures ANOVA. So here's a graphic that I hope makes this make a little bit more sense. The repeated measures ANOVA, also known as a within subjects ANOVA, still has a factor with more than 2 levels, but now each participant is assigned to each level. So we still have a factor here, and we still have groups assigned to different levels of the factor. But from our population, we take a sample, but the same sample participates in each group. Okay? It's the same participants in every level of the factor. Okay? So maybe it's the same test given more than 2 times to assess progress in a concept. Maybe it's having each participant try each condition. So maybe when they are trying to assemble a chair, they're trying to see which instructions work best. So maybe now they would give a person each style of assembly instructions, like text only, a video, text with illustrations. There would be a big risk for a learning effect here though, so each participant would probably be randomly assigned to the order in which they received the instructions. Remember, that was called counterbalancing. The logic and process for the within subjects ANOVA are similar, but they're slightly more complicated than the independent groups, the one-way ANOVA. So what this one does is it compares the between group variance to the error variance. In the case of within subjects ANOVA, similar to the paired sample t-test, we are able to pull out the variance associated with the participants. Because it's the same participants in every group, then all the variables are theoretically the same. So we're removing some of the error caused by the confounding variables that we have when we're testing different people. So we're able to remove some of the error in our study. So we have 3 levels of an IV. With 3 levels of IV that aren't time dependent, we might test participants in every possible order with each participant assigned to one of the orders. Like I said, that's called counterbalancing. This helps eliminate some of the confounds caused by testing effect fatigue example. So for example, if we have 3 levels, we might test someone in the order 1, 2, 3. The next one might be 1, 3, 2. We can put a lot of different combinations of those 3 different levels, and they can experience the conditions in different orders, and it helps remove some of the confounds that we might have. But with 4 levels of an IV, this starts to become more and more difficult. So you see, with 3 levels, we have 6 orders of things. Okay? But with 4 IV levels, then we have 24 possible orders. With 5 levels, we have 120 possible orders. So in this case, it would be probably impossible to make sure that everyone has one of the orders. You would just randomly assign them. So hypotheses in a repeated measure ANOVA, they're the same as a one-way ANOVA. So the null is still there's no difference between the groups. All of our groups will be the same. The research hypothesis is still there is a difference between at least 2 groups. Just like a one-way ANOVA, a hypothesis for a repeated measures ANOVA is always non-directional. It's always two-tailed. We still use the F statistic, and it still takes on the same general form. So it still has this form for if you wanted to calculate it, if you just wanted to have fun and calculate it yourself. Essentially, we're looking at the variance between groups divided by the variance within groups. It's the same form, it's the same calculation. But now I want you to kind of think about there are 3 sources of variance. We talked about 2 sources before, but really there are 3. There's the between groups variance, so if you were to take all of your different groups and find their means, what are the difference in their means? The within groups variance, if you were to look at each of your three groups and see the spread of your data in those three groups, that's your variance. In a one-way ANOVA, we called that our error because we didn't know what was causing that variance. But we also have something that's called a between persons variance. This would just be how each person scores differently on the three measures. Every person is going to be different than every other person, and there's just some unknown there. We don't know why every person is slightly different than the other person. So in a one-way ANOVA, we had the variance due to our groups. That was the factor level. And the leftover variance was the error. We called that the within groups variance. But in a repeated measures, we can now remove the variance between the subjects because all the subjects are the same. So all their variance is the same in every group. So we can get rid of it. It explains a little bit more of our error. And the error term that it's left over, the between persons, is therefore smaller. Don't worry too much about this. You're not going to be tested on it. I just wanted you to kind of understand why a repeated measures ANOVA is slightly better than a one-way ANOVA. By removing some of the error due to the within groups error, because we have the same subjects, we increase our chances at a larger F. And once we have a larger F, we're more likely to be significant. And whenever significance becomes easier to achieve, it means we have increased power. Therefore, repeated measures ANOVA is more powerful than a simple one-way ANOVA. Again, don't worry about it too much. Just remember that a repeated measures is always more powerful than a between groups design. Degrees of freedom. There are different degrees of freedom. The total is K, which is the number of groups, times N, which is your number of participants, minus 1. The factor degrees of freedom is K minus 1. So if we had 3 groups, 3 minus 1 is 2. Our degrees of freedom would be 2. The between persons degrees of freedom is N minus 1. But you don't need to worry about this one. You're never going to have to report this one. This is just sort of the overall degrees of freedom that we're used to seeing, N minus 1. And then the error degrees of freedom, which you do need, is K minus 1 times N minus 1. So if we had 3 groups and 50 participants, you would take 3 minus 1, which is 2, and you would multiply that by 50 minus 1, which is 49, and you would get 98 degrees of freedom. Again, you don't have to hand calculate these. SPSS will do it for you. I just like to give you the equations for those of you who care. But we still report the degrees of freedom factor and the degrees of freedom error. Now in a one-way ANOVA, they were called between and within degrees of freedom, but now they're called factor and error. Okay. Effect size. In a one-way ANOVA, our effect size was eta squared, and we had to calculate that. But in a repeated measures ANOVA, we use something called a partial eta squared. And this is good news for you. SPSS will calculate this one. Why it will calculate partial eta squared for you, but it won't do the full eta squared, I don't know. Just count your blessings that SPSS will give this for you, and you do not have to hand calculate it. So the guidelines for partial eta square, small is about 0.01, moderate would be 0.06, large would be 0.13. So use these guidelines when you're interpreting your partial eta squared. So that's repeated measures ANOVA in a nutshell. Don't worry if you're confused. I'm hoping as we go through some examples it will make sense. I am going to talk about how to do it in SPSS. You obviously will not be having to do it, but at least now you'll have this as a reference. So we're going to just kind of go through how we would do it, and then in the next video I'll take you through some examples. So in a one-way ANOVA, remember the IV was one column with multiple levels. So we would have one column that represented everybody's scores and another column that represented which group they were in. Because remember, every row represents a participant. In a repeated measures ANOVA, each level has to have its own column because every participant is involved in every level. They need a slot for their score on every level of the IV. So we're going to go through an example that was in the textbook. Not your book, just a textbook that I have. So in this example, a teacher is trying to motivate students through either threatening them with bad grades, encouraging them, or giving no comments at all, which is the control group. So, do teacher comments affect student grades? Teacher uses different methods before 3 different tests to remove some of the confounding variables. Maybe the order could be varied by student, so maybe for some students she gives the threatening, for some the encouragement on each test. But this table may be the results of the way it would be entered into SPSS. So you see we have a column for the participant and then a column for each of their 3 different conditions, whether it was the control group, the encourage group, or the threaten level. Okay? So note that each participant is a row and each level of the variable is its own column. So to run it, we go to Analyze like always, but repeated measures is under General Linear Model. It's no longer under Compare Means. Here you have to tell you how many levels are in your factor. So our IV is just motivation, and we have 3 types of motivation. So we put the number 3 into that box, okay? And we add it. So now that we've said it has 3 levels, we have to define what those 3 levels are. So here's where you put in the variables that represent the 3 different levels. So we put in the 3 columns that all represent different types of motivation. Okay? So in this case, order is arbitrary, but it will matter which order you put them in when you're interpreting your post hocs because it'll only tell you 1, 2, or 3. So you need to know which level you assign to 1, 2, and 3. Okay? So in options, this is where we can get our post hocs. It's not under the post hoc box anymore, of course not. SPSS can't be that easy. So you have to tell it that you want the motivate factor. You want to compare the main effects, and here they only give you like 3 options, so I would just tell you to stick with the first option. This is what's important. You have to click on descriptive statistics to get your means and standard deviations, and this estimate effect size is what gives you your partial eta squares. So you have to collect those 2 boxes if you want those. And then it might give you results like this. So here are your 3 different levels. It'll give you the means, the standard deviations, and the number of people. Now in a repeated measures ANOVA, this number should be the same, because there's just 11 subjects who experienced all 3 conditions. So these 11 people are all the same in all 3 of these levels. This doesn't mean you have 33 participants, it means you have 11 total. This is now your ANOVA table. There's a lot of stuff here that looks really confusing. I don't want you to worry about it. There's an assumption about repeated measures ANOVA called sphericity, and SPSS gives you the test to tell you whether or not that's met. I don't want you to worry about that right now, so just always use this row that's called sphericity assumed. So use it here. This is your factor level, and here's your error. Use against sphericity assume. So you see your degrees of freedom here are 2. Here, down here it's 20. Here's your F, 47.43. Significance, that's your P. And here's your partial eta squared. So you would say that F220 equals 47.43, significance, P is less than 0.001, partial eta squared is 0.83, which is large. Then when we get into the post hocs, it works the same way as the post hocs did before, but now instead of putting the names of your levels, it gives you the numbers. So it's important that you know which level you assign to which number. But if you compare these, you can see that all 3 comparisons were significantly different. 1 to 2, 1 to 3, and 2 to 3. All of these were significant, so we would have to report them. Okay? So we're going to talk about how to report those in the next slide. Okay? So we would say type of teacher motivation affected students' test grades, and we report the F results. We just have to give the overall results first. Was there an effect of our IV on our DB? Yes, there was. Then we have to break down the post hocs. When a teacher encouraged students to study, students earned better grades than when the teacher threatened students with poor grades or said nothing at all. So now we've compared 2 of our groups. We've compared encouragement to the control and to the threaten, and we've given the P's for those. Now we have to compare our last group, which says students also earned better grades when the teacher threatened them with poor grades than when the teacher said nothing. Okay, so we have compared, we had 3 groups, we have 3 comparisons, we have to address each of those. So you should have 3 P's. Okay? Remember, there is no one right way to report results. Some people, especially your book, would report the confidence intervals. And then you might see people report the post hocs, you might not. I do want to see the post hocs though, just to make sure I know that you know how to read them. And you might want to include a figure, such as a bar graph. And for the sake of your labs and your lab report, I've included those bar graphs for you. So in the next video, we're going to run through an example. Okay?